Hey everyone. I might be a little in the dark here, but I'll try to move back. I just want to sit here because I have a couple bird feeders back here. There's this one right here is a suet feeder. It's just got a block of suet, which is fat, lard, and maybe some woodpeckers will come while we're shooting this video. Or this one right here is an oriole feeder. It's got an orange hanging there, and so it's been pretty active this morning, and oriole's been coming. I don't know if he'll come when I'm sitting here talking. They get kind of freaked out, but you never know. Maybe a bird will come by when we're shooting this video. So the last time the last lesson we had, we looked at this thing right here. This chart showed the bonds and the energies that were needed to break or make those bonds. So we had this potential energy curve. The atoms are far away, like this, when they are in these positions here. So if I have an atom here and an atom here, they're far away. We're higher up in energy, but then as we bring them together, remember when we bring them together, they are down here. So I have two atoms, they'd be down here together. So lower energy when they're together. Break them apart, higher energy. Okay, so I break them apart, I put in energy. We talked about that. And so this chart was kind of a starting point at where, how the energy goes when you start breaking bonds. It turns out that scientists did a lot of research, and they figured out how much energy different bonds takes to break. And this is a table that they have. So what I'm going to do is, if I look at this table, the first thing is there's numbers on here, and they're a lot higher than the things that we saw on that simulation. And the reason for that is the way they measure it is in like kilojoules. So it's 1,000 joules is in 1 kilojoule, and it's hard to measure one bond, and so they measure a bunch of bonds, and they use this number called the mole. You don't have to know about that, but it's just basically like millions and millions and millions of bonds, and they figured out, well, this is about how much energy it takes to break that many millions of bonds. Okay, so each bond, HH, HC, HO, those have some energy, and I just want you to first look at patterns of how the bond energy right here, how does that relate to the length of the bond? So different bonds, as you saw, have different lengths. You know where that dip was in if I go back to this screen here. So the dip for different bonds was in different places. It's here for CH, but then for something like OO, it was something like out here, right? So that bond length is farther out. The bond length for CH is closer in. So there's different places for these bonds. The first question is, how does the bond energy and the length of the bond relate to each other? So look at those two things, write out some patterns that you see there. The second thing that I want you to notice is the types of bonds. How does that relate to the energy? So it turns out that there are multiple types of bonds that are present. There is something called a single bond. So if you have one line there, that's a single bond. And if you have two lines, it's a double bond. It's actually two pairs of electrons that are being shared there. So this here is a double. And then this is a single. How are those bond lengths, and then how are the energies compared to the types of bonds? This thing here is a triple. So, look at patterns and see how much energy does it take to break a triple bond compared to a double bond compared to a single bond. Look at those and then answer that question down there. Okay, hey, welcome back again. So it turns out that uh, no birds came because they're scared that I'm sitting right there. So I moved. This is the other feeder. This one has a little bit more traffic right now. I also have this. I can't point with my finger. This one right here. So this is an Oriole feeder too. It's got jelly in it. We'll see if something comes of that. So anyway, the the next thing we need to do is we're taking our models, and it's, as you found out, I've talked to a couple students. These models are kind of difficult to use because they fall apart all the time, and it's hard to represent them in a on paper. So this is CH4, if you remember. This is CH4, and these are O2. This is what we started with, oxygen. So you had two molecules of O2, and we're going to translate that to paper now. So CH4 is this one right here. That looks like this. So CH4 is methane. We're just going to draw it with a C in the middle and 4 lines sticking out of it. That's going to be our first molecule. Our second molecule is going to be the 2 oxygens. And it turns out that oxygen actually has a double bond. So it's got 4 electrons shared between the 2 oxygens. And so we're going to draw it with 2 lines. I know that we just had the one toothpick in there for our model, but it's easier. The toothpicks you saw, if I had 2 toothpicks in there, it would have been just a mess. So this is how we're going to draw our pictures for methane and oxygen. And this is how we're going to proceed as we move forward in this lesson. Oh, there's something right there. You see that? That is a female rose-breasted grosbeak. They migrate up with the orioles around this time. So it's kind of brownish color. It's like a giant finch, but the male grosbeaks are black with a little red underneath. That's why they call it rose-breasted. So maybe we'll see something a little bit later. All right. Oh, so there is a rose-breasted grosbeak out there right now. Let's see if I can. Where's my camera? I don't know if you can see that. Right here. That is a rose-breasted grosbeak. Okay. I'll move the camera a little closer. That's a male grosbeak. He's got a little rosy spot right on his chest. He's dark on the top. There's a cardinal there. Now he's kind of main. Whoa, holy cow. They're like going at it. I guess the cardinal and the grosbeak do not like each other. So there you go. You get to see a couple of the birds here. Hey everyone, welcome back. It's been a long day. I just got back from birding for a really long time and saw a lot of cool things. But I need to finish this video because otherwise I'm going to forget what I was going to talk about. So anyways, I told you we have these molecules. We draw them now as pictures. And every time we have a bond, so the bond energy that we saw before on the simulation, those were kind of like one bond, but now we have lots of bonds. We're just going to use these numbers here. This is the bond energy for oxygen in kilojoules per mole, which is just a lot of it. Just think of the mole as we have a lot of bonds. Okay, so we've got a bunch of bonds, and if we're going to break oxygen, it's 498. Now, how many bonds total are we breaking in this picture? So for oxygen, we're just going to, this is one, we're going to count it as one bond. We have another one here, another one bond. So here, on this table, you're going to use a 2 here. So you type in a 2, and then the total energy to break that, well, We're going to take these two numbers and multiply them, and you're going to get whatever it is that equal here. Okay, so type that in. Same thing with this now. So we're breaking all these apart for CH. Well, how many of these? Just remember that CH and HC are the same thing. So we have these here. So you write that in, multiply that out. And then when you have these two in this section here, you make that, you add it up. Okay, so you add these two up, and then you get this number here. Okay, so that's the total energy. You're going to break all those bonds. Now, what do we do when we have those atoms all flying around, and then they're going to come back together? So we are going to represent them now as, the molecules that we have. We're going to use these pictures. And so instead of using the model kits again, we're going to draw the pictures. Turns out that carbon and oxygen in CO2 have a double bond. There's actually two double bonds. So when we make these new bonds like this, so we have this bond here, and this bond, and this bond, that's going to be, so you take that, add them up here, and then you multiply them out, and you get this number here, okay? For carbon and oxygen, this is one bond. Okay, so this is one bond. So this is actually going to be 2 on here. And you multiply that out, and then you get that. That is the energy. Now remember, when we make a bond, snap them back together, that drops down in energy. So we started up here. Remember, we go down because it gets nice balanced bond, and so it's stable, and we release energy. So we get rid of that energy. These two numbers now, we're going to add them up, and we're going to get this total down here. Okay? So now, once we have all those, we have one number here, we have one number up here, okay? We're going to take those two numbers, and we're going to make sense of these two numbers. We have some energy going in. How much energy is going in? Put that number in here. How much energy is coming out? Put that number in here. And now we're going to start looking at something called an energy diagram. So there's a way that the energy diagram works is you start at 0. Okay, so this is potential energy on the y-axis. And we start off with methane and oxygen at this point. And it's just a starting point. We just stuff sitting around there. Okay? And once we break the bonds, that is energy in. So this is going up like this. So we're going to draw an arrow. This is kind of this distance right here from here all the way to here. That is the energy from here to here is energy in. Whatever that number is here, write that number in here. That is energy in. So we go up a hill like this. We go up the hill like this. Not very good at drawing. And down here, this is called the reaction coordinate. It's a fancy name for just how the reaction's moving along. So we start here. This is my starting point. This is my midpoint. Everything's broken apart. Okay? And then once we have the energy in, well, now we have energy coming out. And that's recalculated for the second time. So type in your energy out here. And then we have two scenarios. So the first scenario is the energy out going to be something like this, where we have a short arrow. Okay, so we're going to go down to here. Are we going to go down this far? Why or why not? Why do you think, so take a look at this arrow, how long this is. Do you think this is going to be the distance that it's going to drop down by? Or do we have this scenario where the arrow drops really far? So we have our energy out. Is the arrow going to drop really far down? Why do you think those? So think about that. Type in your answers. I'd love to see your thinking, and then the next time we'll discuss more about this.